But I also promised to explain to you how it is that you can make images from text or images from noise and even music from noise. So in order to do that, we need to go one step deeper. I'm going to explain in a simplified way what a neural network actually is. And again, in practice, very complicated. In theory, not that complicated. So the neural network is loosely based on the biological neuron that we have in our brain. And it looks something like this in a cartoon. So you have these little arms on the yellow part called dendrites. Those are the inputs. Let's say that they get electrical signals from your retina. So lights hit your eyes, they're electrical signals. They go into these dendrites in the yellow part. These things combine. So let's say that this particular neuron, it is looking for vertical lines. That's a vertical line. Or horizontal lines in front of your eyes, right? And so maybe this particular neuron, when it gets a pattern of these electrical signals, these dendrites, they get a value, it's going to hit some threshold that says like, hey, I think I'm seeing a vertical line here. And then it's going to send a spike along this axon to the right. That goes to the next layer of neurons, that goes to the next layer of neurons. This is all that a neuron does. It takes a few input signals, it combines them, and if it hits a certain threshold value, it's going to say, hey, I'm seeing something here, and it's going to send a signal or a spike. So what computer scientists did was they did a very simplified, idealized mathematical version of the biological neuron called the artificial neuron. So the arrows pointing in here are the equivalent of the dendrites. So you have A1, A2, A3. These would be the electrical signals from the eyes. In a computer world, they would be the pixel values from a camera. They come in, they get multiplied by these things called W1, 2, 3, which are weights. I'll talk about that later. And then as you take the electrical signal, you multiply them by the weights. If this cell body, the circle in the middle, hits a certain threshold, for example, the cell says, I think I see a vertical line, it is going to send a spike or a signal to the right called Z. So it's a very simplified version of what the biological neuron does. Okay, if you didn't fully get that, don't worry. You'll see it in practice now. Let's say that we have a picture of a cat. Why not? The internet is full of cats. Now, let's say that you take a camera and you take a photo or a video camera and you point it towards this cat. What the computer is going to see are pixel values. Remember, the computer, everything is numbers. The pixel values are just numbers. Maybe we simplify it and say it's a grayscale. So number 0 is black and the number 255 is white. And in between there's shades of gray. So just numbers. So now you put up a bunch of these artificial cells. And each of these inputs gets a pixel value. And now you can imagine that maybe the top neuron there, it is going to spike if it sees maybe a diagonal line like this, right? And it says like, hey, I see a diagonal line. And then the neuron below it, maybe it's looking for a diagonal line in the other direction like this. And it's only going to spike and send a value to the rest of the network if it sees that. And now you add a second layer of network. This is why they're called deep neural networks. You add more and more layers. And so now the second layer of neurons, it can get a spike from the first layer and says, the first layer saw a diagonal line like this and a diagonal line like this. And the second layer neuron is going to spike only when it sees both of those in the first layer. So maybe this is actually the shape of the tip of a cat's ear. And maybe this line is the shape of a whisker. And so you go one more layer and it combines all of these signals. And at the very end of this layer, which can be very deep, the last neuron would actually say, I see all the inputs from all of these layers of what is actually a cat. And now you have what is called a cat classifier. So how does this work? Well, if you look at this, you can almost intuit that if you have all of these weights, the W1s and 2s and 3s, if you had infinite time, you could imagine sitting and tweaking all of those numbers so that these neurons happen to hit that threshold and spike exactly for the shape of a cat from many, many different directions, right? So some of these neurons are looking for tips of ears, some are looking for neurons, some are looking for eyes and paws and so forth. You could imagine that if you had infinite time, you could tweak all of these parameters in the network so that it only spikes all the way back to the end when there is a cat, but not when there is a car or an aeroplane or anything else. So again, in principle, not that hard to intuit. In practice, pretty complicated. How would you tweak these parameters? Because there can literally be many billions, almost up towards 1 trillion now of parameters in a network like this. But we're on the theory level where things are simple. So again, there's one thing you should understand here. Scientists actually a long time ago came up with something called backpropagation. And what that means is they found a way for the model to teach itself all the right parameters. And the way to think about this is you have a lot of pictures of cats and things that are not cats. And instead of a human sitting and tweaking these parameters themselves, what you do is you just initialize all these parameters as random numbers. It's completely random. So if you think about it, the first time you show this network a cat image, it's going to guess completely wrong. By definition, random, right? But it also means that by random chance, sometimes when you show it a cat, it will actually guess that it was a cat. And then what you do is through something called backpropagation, you say like, hey, wait a minute, you happen to guess correctly. Keep those values. In fact, move all the W values a little bit in that direction because you were right. And then when it guesses wrong, you do the opposite. You move them in the other direction. And then you do this for literally tens of thousands, hundreds of thousands, millions of images, where you say like, is this a cat? And it says yes. And then you say, good network. Move all these values a little bit more in that direction. Then you show it maybe an airplane, and it says it's a cat. And then you say, bad network. Move all the values a little bit in the other direction. And you just keep reinforcing it. And if you do this millions of times, eventually all of these parameters, because you reinforce the good behavior, are going to end up on finding exactly the combination of shapes in this image through multiple layers that represents a cat, but not a dog and not anything else. So this is what a neural network does. Again, it's quite simple in theory, even though it was hard and took a long time to do in practice. So this is important to understand, because when you understand this notion of taking numbers, multiplying them, seeing if they go over a threshold, then taking those numbers, multiplying them, now you can understand how these image generation networks and so forth actually work. So here's another concept that I think is very interesting to understand. Intelligence is compression. Now, this is stated as a fact. It's not a proven fact, but it is a theory that a lot of people have, that one way to think about intelligence is as compression. What do I mean with that? Well, back to intuition. If you speak to someone who knows something very well, they're usually very good at explaining it, right? Whereas if you speak to someone who doesn't know something very well, it's hard for them to explain it. So the person that knows something well can explain something in a simple way. That usually means that if they can explain it in a simple way, they understand it better than if they can't. So already there, you can see that there's something around compression, right? Probably that person spent a lot of time on this problem, and they learned to take all the details and compress it into what it actually means and understand it deeply. And then all of a sudden, they're able to explain it. So there is actually even this thing on the internet called the Hutter Prize, which is a competition where you're supposed to take all of Wikipedia and try to compress it as much as possible, including its own extractor actually, without losing the information in Wikipedia. Because the idea is that in order to compress Wikipedia effectively, the system that compresses it is going to have to understand a lot about the world. Like, you have to be smart in order to compress. You have to understand the dimensions of the world really well to be able to compress the world. And like I said, this is intuitive. Humans that can explain things simply, they usually understand more. So the system that compresses it had to develop understanding. So think of intelligence as a side effect, a necessary evil of being able to compress information. So in this Hutter Prize, you can actually make money for every percentage that you can compress Wikipedia. in that case, losslessly without losing any information. But in general, the concept is if you can compress something and retain most of the value, you probably understood it really well because you could represent the same thing with less information. And representing something with less information kind of requires understanding on the part of the system that compresses it. All right, let's get a little bit more practical here. So remember, to a neural network, everything is just numbers. Language is numbers, pixels are numbers, samples are numbers, DNA sequences are numbers, anything is a number. So if we take this neural network that looks a bit funky, let's say that we take a sentence like a cat jumping out of a window, which then again will be represented as a sequence of numbers. So 1, 2, 3, 4, 5, 6 numbers. And then what we do is this neural network is just take those 6 numbers, and through these neurons it multiplies it and adds it, and has it represented by fewer numbers, then multiplies and adds it again, and in the middle it only gets 3 numbers to represent those 6 numbers. I know it seems weird, but hang on. So we force the network to take 6 numbers that represent the full sentence and represent it with only 3 numbers. And now you ask the network to do the opposite. From these 3 numbers, again, it multiplies it and tries to turn it back into 5, 6, or 7 numbers. In this case, 1, 2, 3, 4, 5 numbers. So all we did was we told this network that here's a sequence of numbers. That to us means a cat jumping out of a window. You have to compress those 6 numbers to 3 numbers and then expand without any new information, just from those 3 numbers, back into the same sentence, or as close as possible that you can get. So the entire training task here is to take a sentence, compress it, and try to recreate the same sentence. So in a perfect world, the output would be a cat jumping out of a window, the exact same as the input. So you train this network again and again to try to compress these numbers and recreate the same numbers. And it's not going to be possible for the network to recreate the same numbers perfectly, because when you go from 6 to 3 numbers, you will lose information. So by definition, you lost information. You lost at least those 3 numbers from 6 to 3. So it's going to do the best it can. And that means that it's going to have to pick these 3 numbers in the middle, back to dimensions. It's going to have to pick the 3 dimensions, the 3 numbers, that sort of best describes the world. What do I mean with that? Well, it means that if you look at something like a cat jumping out of a window, maybe these 3 numbers in the middle, they represent something like not quite a cat, that's too detailed, but maybe a pet. And maybe the second number represents something like going in and out of something. And the third number represents something like an entity or a house. So what you will get on the output is something that is similar conceptually to the sentence you put in, but not quite the same because information was lost. So if you put in a cat jumping out of a window, maybe what you get out is a pet leaving the house or a dog leaving the house, right? Because the system had to pick, it had to lose information, it had to abstract, it had to pick the most important dimensions to do as well as it could. It had to compress. So what this means is that this thing in the middle, the embedding code, again, the vector, hopefully, if you do this right over a lot of sentences, is going to find the numbers that are the best representation of the world that is being trained on, which in this case would be the text of the internet, right? It's a textual world for this network. This is called embedding. So you take the sentence and you embed it from 6 numbers into 3. And the network, if you train it correctly, is going to choose the right dimensions that give the most information about the world, that completes the training task the best. So again, it seems like a pretty useless task, especially for language. Why would you want to get like a different version of the same sentence out? But maybe an example that would be easier to understand right now. This is important to understand for the diffusion models. That's why we're going through it. So if you instead think about images or maybe video, you could imagine on the left side here that you have an image or a video that takes a lot of space. And when it comes to images, you know that you can compress it and actually lose a lot of information, and it's still good enough, right? This is what all image formats do. They compress the image, so that you can send it over the internet using much less data than the actual original image. So one way to create that compression would be that you take an image, for example, of a cat on the left, you force the network to take all those numbers, all those pixel numbers, and represent them there in the middle with much fewer numbers, and then just try to recreate the same image of the same cat as well as it can. And if you do this right, it's going to be very good at recreating almost the right image. And if you teach the network to do it as well as possible, it's going to find the dimensions that are most important to keep there in the middle in order for a human to think that this is still the same image of a cat. So the network is going to learn itself to compress to the most important dimensions. For example, humans tend to care a lot about low frequency things in images and not as much about high frequencies. So we'll probably learn to keep some of the low frequencies and not the high frequencies, etc. But it's not important with the details. The whole concept is it takes a bunch of numbers, in that case of the image, pixel numbers. You force the network to try to pick the best representation with much fewer numbers that still keeps as much as possible about the information in that original image, and then recreate it. So if you do that, now you actually have a compression algorithm where you can take an image, but instead of sending the image over the internet, you just embed it and you just send this code in the middle. And the receiver has the other side of this network and then decodes it back into the full image. So now you saved a lot of bandwidth. This is called an autoencoder. And it is actually how some compression algorithms are done on the internet. So now you not only understand what a vector is, what a word vector is, but you also understand how you would actually create this vector and what an embedding is, which is a network that through training takes a piece of text, an image or something, and automatically creates this vector for you. And it automatically, importantly, chooses the best dimensions. Instead of having 600,000 dimensions of the world, you force it to choose much fewer, and in forcing it to choose fewer, you force the network to actually become intelligent, at least according to some definitions of intelligent, in how it picks those dimensions. All right, we're almost there. So what about images, music generation, video, etc.? There's only one last thing you need to understand now, that you understand all of this, in order to understand how something like Stable Diffusion works or Midjourney or something like this. And that is this notion of diffusion models. So diffusion models is actually also something that I think conceptually is very intuitive. So remember this neural network, right? Let's say that you take an image, the one to the left here called T0. And what you do is you just add a little bit of noise. So you go from the image on the left to the second image on the left. You add a little bit of noise on top of this image. And now you train a neural network to simply try to find that noise and remove it again. And if you look at those images, the difference between the first and the second image is very small. It is intuitive, I think, to you that you could remove that noise if you just had time. And so why couldn't a neural network? It doesn't seem that hard because you just add a little bit. So that's the first step. So think of it almost as you have a separate neural network that just removes a little bit of noise from the second back to the first image. Now you take the second image with a little bit of noise and you add a little bit more noise. And now you train a network to just remove that additional noise. Like the image that you added the noise that you added to the third image back to the second, not all the way back to the first. It's just one step at a time. So every step here is just removing a little bit of noise. And now you take that third image, you add a little bit more noise, you train a network to remove just that noise. And you keep going. You take that image, you add more noise, you train the network to remove that additional noise, etc. And when I say remove, you train a network to identify this was the noise added and simply deduct it from the picture, sort of recreate the original image. So hopefully it's intuitive that you could do this. So you have like a network that can take an image at any stage and remove that additional little noise. Because if you think about it, at every stage, it was a deceptively simple little task. But at the end, you've added so much noise that there is pure noise in the image. There is no image anymore. So to the right, the task is actually to remove the last piece of added noise from complete noise to almost complete noise in the second to last image. All right, so again, this seems like a stupid task. Why would you take a perfectly good image and destroy it slowly and train a network to remove a little bit of noise at a time? Well, the really cool thing is now you have this network that starts with a good image, learns to remove a little bit, makes the image worse, removes a little bit again. But if you now take this network and you kind of run it backwards, so instead of taking the neural network that is furthest to the left, that removes just a little bit of noise from the good image, you start with the one to the right that removes a little bit of noise from the pure noise image. What you can do is this. You start with just random noise, and then you run the network backwards. And what will happen is essentially, what you've done is you've trained a network that is desperately trying to look for sort of face-like noise in an image. And so it takes this complete noisy image, and even though there's nothing there, it's going to say like, hey, I've been trained to find sort of a face-looking noise in here, or if you want to simplify, I've been trained to find the rough outlines of a face in here. I think I see something there. And it's going to remove a bit of noise that actually makes it look a little bit more like a face. And then in the next stage, the next sort of network, even though it's the same network, but think of it as separate, takes that image and says, I've also been trained to remove noise, to find like face-like noise here and remove it. I think I see the outlines of a face in there, even though there's hardly anything there. In the first stage, there was nothing there. It was just noise. In the second stage, there is actually a little bit of a face there because the network itself removed exactly the pixel that made it look more like a face. And now the next step says, hey, wait a minute, I see the outlines of a face. I'm going to remove, I've seen this before. I'm going to remove this noise, which is going to make it look even more like a face. Third image takes over, says, oh, I clearly see the outlines of a face here. I know exactly what kind of noise I should remove to make this look even more like a face. And you just keep going. And at the end, all the way to the right, you will have created a face out of pure noise, meaning a face that actually never existed. So to be clear, not a copy of a face that existed. You train this diffusion model to remove noise across, millions of different faces. So it didn't learn to create a specific face. It learned to create general faces, and is looking for general face-like noise in this first random noise image. And so this is how you get to something like this. This is a site called thispersondoesnotexist.com. That every time you go in there, it literally generates very believable faces of people that never existed. Now, for those of you who know more about this particular site actually doesn't use a diffusion model. It uses something called a GAN that came before Generative Adversarial Network. But the idea is the same. Diffusion models have sort of taken over from GANs. So now we know how we can generate at least faces out of pure white noise, like one particular thing. But I promise to explain to you not just how you can create one thing, but how you can do something like what Stable Diffusion or Midjourney does. And on these services, you can do more than just get many versions of the same thing, like a face or something like that. You can put in text, and you can ask it to generate, for example, a picture of an astronaut riding a horse on the moon, which is something that you can Google, for example. And so how does that work? How does this text conditioning work? Well, it is a diffusion model. So it does what I just showed you, but it does something more. This is why you just learned about vectors. So let's go back to this thing of intelligence is compression and how you actually condition on text. So I showed you this network that we said looked pretty useless, where you take a sentence, you sort of compress the numbers in that sentence to fewer numbers that hopefully somehow captures the important dimensions of that sentence, and then you try to expand it to the same sentence again. And we said it was pretty useless, but now it's going to turn out to be pretty useful. So what you can do once you train this network is you cut off the right part and you just keep this part. So now you have a machine that you can give a sentence in English and you can ask it to embed it, to compress it to these numbers that represent what is in that sentence as well as possible. Okay, so now let's imagine that you're a service, let's say a social network or search engine that has a lot of examples of images and captions to that image. So for example, maybe a picture of a cat staring at you and the caption, a cat staring at me. Now what you can do is the following. You can take that caption, a cat staring at me, and you can take this encoder. You can take that sentence, which then again is just a sequence of numbers, so 1, 2, 3, 4, 5 numbers. And you can ask this network to compress it into these 3 numbers that hopefully captures what it means to be a cat staring at me. And now we take the diffusion model, so we take the image that belongs to this caption. As before, we add a bit of noise, then we add a bit of more noise, then we add a bit more noise until it's complete noise. And we put in this neural network in between that is going to try to remove the noise. Now this is exactly what we did with the faces, right? So if we just did this, we're going to build a diffusion model that always finds cats staring at you, which is not what we wanted. We wanted something that is steerable. So we're going to do one more step. We're going to take this other network we had that takes the sentence, a cat staring at me, embeds it from these 5 numbers into these 3 numbers, the code, the pink thing. And as this diffusion model is trying to remove the noise between the second and the first picture, we're going to give it these 3 numbers as a clue, right? So remember, we're giving it the picture of a cat staring at you, and we're giving it the 3 numbers that represent a cat staring at you. So you can think of the diffusion model now as having a clue about what kind of noise it's looking for. It's not just looking for one type of noise. It's going to say like, hey, these 3 pink numbers, I've seen them before. It means there's probably a cat in here, or there's probably cat-like noise here. And then you do that, and at the next step, you give it the same clue, like you're still looking for cat-like noise. The next step, you give it the same clue. Remember, to a neural network, everything is numbers. The pixels are numbers, but these sentences are also numbers. It doesn't really understand that one is images and the other is text. It's just saying like, I've seen these numbers. When I saw these numbers with these 3 numbers on top, there was always cat-like numbers in there, or cat noise-like numbers in there. So let me try to see if I can find a cat in here, staring at me. So you do this, for example, for this image, a cat staring at you, and then you have other similar images, but with different captions. So instead of a cat staring at you, maybe another image is a cat jumping out of a window. And now this encoder at the top is going to embed that sentence, which is 1, 2, 3, 4, 5, 6 words, 6 numbers, into 3 numbers. These 3 numbers would probably be similar. There's cats in there, right? But there's also the concept of jumping, and there's not the concept of staring. There's a concept of window and so forth. So this vector will be similar in the dimensions, but a little bit different. And now you do the diffusion on that image. So again, the network has this clue, these 3 numbers, as it's trying to remove the noise, so that it can understand what kind of noise it's looking for. So remember, in the first process, we always removed the same kind of noise, face-like noise. But now we're doing a diffusion model that gets a clue for what kind of noise it's looking for. And so we're very focused on cats here, but this could be anything. It could be a picture of an aeroplane and the text saying an aeroplane flying. And then it's going to kind of learn what aeroplane-like noise looks like, or the removal of aeroplane-like noise. And what you can do is you can actually take something like a song, right? A song is an audio wave, but it turns out you can take a piece of audio and you can transform it into what is called a spectrogram. So a spectrogram is the visual representation of a song. It kind of says how much of every frequency is in a song at a certain time and the magnitude of that. It doesn't really matter. If you just imagine that you can take a piece of audio and transform it into a spectrogram, you can represent audio as an image. So now what you can do is you can take a song, for example, Obladi Oblada by the Beatles. You can take the spectrogram of that song, and you can take the description in text, literally, Obladi Oblada by the Beatles, or maybe a song, the song Obladi Oblada by the Beatles. You embed that, so now the code is going to somehow represent the concept of a song, the concept of the Beatles, and some other things that we don't fully know. It's going to find the best representation of this sentence. And so now you're giving that sentence, the song Obladi Oblada by the Beatles, as the clue to this diffusion network as it is trying to find this spectrogram. And so you're going to teach it to first of all, find spectrograms, but you're also going to teach it, if you show it many spectrograms with many different types of music, a certain type of spectrogram. So what happens now is once you train this network on millions of different types of images, as I said, cats, dogs, airplanes, images of music, whatever you want, you can now take this network, you can turn it around, and you can start with just pure white noise. So there is no structure in here. There's literally nothing in this picture. And now you take a sentence that never existed. Let's say an Avicii song in the style of the Beatles. And as you've trained this network, this encoding process hopefully will have captured the dimensions of the world. So we'll know what Avicii is and what it means. It'll kind of know what a song is, that it should do a spectrogram now and not a picture of a cat, and sort of what the Beatles represents and what those kinds of spectrograms look like. And so it's going to embed this into this code that in our simplified example is just 3 numbers. It's not 3 numbers in reality, it's more numbers, but for purposes of simplicity. And now we take this pure white noise, we give this code as a clue to the diffusion model for what kind of noise it's looking for. And the interesting thing again here is now we're telling it to look for a kind of noise that actually never existed before, Avicii song in the style of Beatles kind of noise. And it's going to try its darndest to try to find that kind of structure in this pure white noise. So it's going to remove noise that makes it look a little bit more like a spectrogram or song of Avicii in the style of the Beatles. And at the next step, we give it the same clue and say, try harder. Try to really look for the structure of an Avicii song in the style of the Beatles. Remove some more noise. And we do it again, and we do it again. And if you're interested, in reality, these diffusion models have about 50 of these steps. And at the end of the line, at the 50th step, you're going to get a spectrogram of a song that never existed, that hopefully is an Avicii song in the style of the Beatles, when you transform it back from a spectrogram into pure audio. So now you're finally there. Hopefully, you'll be the judge. Tell me what you think. You have some intuitions about how it is actually possible to create new novels, poems, images, even music out of just text or even white noise. And hopefully, you feel like we managed to debunk this conspiracy a little bit. Thank you very much for paying attention.